Hey everyone, my name is Ethan Jones, and this is my Physics 2211 Lab 4 about oscillations at Georgia Tech. So, for the purpose of this lab was to measure the motion of a spring and compare its predicted and measured motion and energy. The models we used were Newton's second law and the conservation of energy, or the energy principle, and the results were the energy is conserved and the motion can be predicted. So here are the models. So I used Newton's second law, which is F equals ma, or F net equals all the forces added up. So I use this because we are measuring motion, which requires an understanding of the net force. I use the energy principle, which is change in energy equals work, which equals change in kinetic energy plus change in potential energy. So I use this because I use this to measure the changes in the energy of the system. I also use the velocity update formula and the position update formula. So here's the experiment that was given to us. So as you can see, we're measuring the motion of an oscillating spring here. So for the conditions, the system was the spring, the earth, the mass, and everything. And since everything was in our system, there is nothing in our surroundings. For the initial conditions, the mass was 0.402 kilograms. The position was very close to zero. The velocity was 0 meters per second. The constant K for the spring was 0.683 newtons a meter, and the relaxed length is 0.123 meters. So for the experiment, we observed the motion of a mass oscillating on a spring while swinging in an arc, and I used a pre-recorded experiment for my data, and to get quantitative results, I plugged this in a tracker. I then uploaded the X and Y positions to a spreadsheet to use in my code. So here's the code. Everything underlined in red is something I changed. So I put in the initial mass and the initial position of velocity, put in the gravitational constant, the spring constant, and the relaxed length. And then I found L by doing the position of the mass minus the spring position, and L hat, and I found S for the spring, and then I found the system energies by using their formulas for kinetic energy, potential gravitational, and potential spring energy. Then I add these all up for the total energy. And then I made a loop while time was less than the time that I observed. So I defined the initial energies here at the top by just setting them equal to what I already solved. And then I found the force of gravity, the force of the spring, and then I found F net by adding these together. And then I used the velocity update formula to get the ball's new velocity, and the position update formula to get the new position. And I used V final for the position update formula because this force is not constant. Then I updated the spring. I found L again, L hat, and S. And then finally, I found the changes in energies. So I found the kinetic energy and then delta K by doing the kinetic energy minus its initial kinetic energy. And then I solved for potential gravitational, and then I found its change. And then I found potential spring, and then I found the change of that. And then total energy equals the sum of all the energies. And then for the change in energy, I added up all the changes in energies. So here are what my graphs look like for the X position versus time and the Y position versus time. The blue is the model and the red is the experiment. So for the similarities, the motion oscillates at nearly the exact same rate in both the predicted and observed graphs. For the differences, the graphs are slightly offset. The model seems to be slightly ahead of the experiment. So for possible sources of error, this could be from starting the data observation too early in Tracker, or issues with the code. There could be a bug somewhere that I don't know about, or maybe I didn't perfectly select the center of the mass each time in Tracker, and this could have just caused minor errors throughout. So what does it mean in part 1? So here's the graph of the change in energy versus time on the right. So as you can see, the energy principle is satisfied. At each moment, if you subtract the bottom from the top of the graph, which is the energies, it will equal 0. And this can also be seen by the delta E line, which is the yellow line. The total energy of the system never changes, so the energy principle is satisfied. So as mean part 2, the oscillation period for the x position data is 1.3 seconds, and the period for the y position is 1.24 seconds. These periods are slightly different from each other because they have slightly different constants k. The spring constant is slightly different for x and y because it may be more or less stiff in one of these directions. All right, for the conclusions, even the most complex motions can be predicted using Newton's laws of motion, and the energy principle will always be followed, and the change of system energy will be zero unless acted on by its surroundings. All right, thank you for watching, and have a good day.